Hello. In this video, we are going to look at how to do a power analysis for correlation and for multiple regression. So for starters, we're going to be using these two packages. And let's begin with the simple case of correlation. We have two variables. We want to do a power analysis. Just like before, if we hold constant the alpha level and whether it's one or two-tailed, then it is the case that if we know or if we're willing to assume any two of these values, we can calculate the third. So this would be the sample size, the power, and the effect size. And for correlation, the effect size is Pearson's R. So let's start with a simple example. Say I'm planning a study for the first time, and I want to have a 90% chance of a significant result, and I think the effect size might be somewhere around 0.2, and I want to know, what does my n have to be in order to have 90% power? Well, if that's the case, you can run this, and you can see you need 258 people. Okay, cool. Now, suppose on the other hand, you realize, oh no, I'll only be able to run 200 people. How big does the effect size have to be in the universe in order for me to have 90% power? In that case, I'm going to enter null, or I'm going to leave blank the effect size because we're using the other two values to compute the third, which in this case is the effect size. In that case, I see in the universe, the correlation would actually have to be 0.23 for me to have a 90% chance of detecting it with just 200 participants. Cool. Now let's suppose that I think that maybe in the universe, let's say I want to compute the probability of a significant result. So I'm going to enter null for power, and I think that potentially the effect size is, I don't know, let's say 0.3. Let's be optimistic. Maybe it's a bigger correlation than we expect. And in that case, I can compute that if the population effect size is that big, we'd actually get a significant result almost every time, 99% of the time, if we ran a sample size of 200. Cool. So that is just meant to illustrate that if you are willing to assume any two of these, you can calculate the third. All right. Now, things are a little more complicated for multiple regression. Mainly because we have a lot of predictors, and those predictors themselves may be intercorrelated. Now, I'm going to show you a workable approach here. However, in the description, I've linked to a video where I go really in depth on how you can use the simulations in R to define really any analysis that you could ever think to run, you can compute power for. And this would include power for simple effects, interactions, main effects, anything that you could analyze, you could compute power for using the magic of simulations. That's complicated and takes a while to learn, but it's also a lot of fun. So if you're curious, follow the link over to that. But for now, just to keep things simple, we're going to use this function called MRC from power to people. And what's really great about this is it lets us work entirely in standardized units of Pearson's R. And so we have to tell it the sample size we plan to run and our alpha level, and then a set of correlations that we are willing to assume for the population. And the first set of correlations here, by the way, this is for a multiple regression with 3 predictor variables. This package can handle up to 5 predictor variables. The logic just expands outward the way you'd expect. For this case, we'll just have 3 predictors. And the first thing we need to tell it is what we expect the correlation is between predictor 1 and our outcome variable of y, between predictor 2 and our outcome variable of y, and between predictor 3 and our outcome variable of y. So we give it our estimated correlations for those pairs of variables. And then because multiple regression operates by controlling, statistically accounting for the other predictors, we also need to tell it the correlations between our first predictor and our second predictor, the correlation between our first predictor and our third predictor, and the correlation between our second predictor and our third predictor. And in this case, I've just entered some small but meaningful correlation values just to illustrate this. Of course, in real life, you'd enter what you expect here. And in this case, assuming these patterns of correlations and with a total sample size of 100, the first part of the output gives us r squared. That's the power that the overall model, the entire set of predictors together, the omnibus test of all of our predictors, the probability that that will be significant is 96%. Now that's great, but presumably we want to learn something about the specific predictor variables that we're using, and so we may be more interested in this output down below. Maybe one of our predictors, whichever one we entered first, is the one we care about the most. Well, in this case, we'd have only 76% power for that first predictor, and of course 63% for the second and 35% for the third. Now, maybe the third predictor here is just a covariate that we're not really all that invested in detecting an effect for, but we want to include it in the model for completeness and to adjust for that variable. So it's good that it's in there, and it might not bother us that we don't have good power to detect that variable. Or maybe it really would. Maybe that's an important variable for us. In any case, I hope you can see that it's incredibly useful to have a power analysis here that tells you about the power for all of your predictors rather than just one of them, which is something you might get from a program like gpower, which is okay as far as it goes. It just doesn't go that far. The other nice thing about this is you're working in units of Pearson's R, which is something that's pretty intuitive for most psychologists to work with. The other problem with gpower is it often works with and gives us output this f squared effect size, which is just not intuitive or meaningful for most people who are working with these variables. And in fact, I don't know if I've ever seen it used outside of the context of power analysis, which makes me question how informative it is. So this, I think, will get you a lot farther. So there you have it. That is how you can do a power analysis for a basic correlation between two variables, or for a multiple correlation involving several variables. There you have it. I will see you next time.